Hey, it's Zach, and today we're talking about bipolar junction transistors. So enjoy, and don't forget to like, subscribe, and click on the notification bell for more electronics videos. Bipolar junction transistors, or BJTs, are transistors that have three leads: a base lead, a collector lead, and an emitter lead. They come in two main types. There is the NPN type, where conventional current flows from the collector to emitter, and conventional current flows into the base to turn it on, and the PNP type, where conventional current flows from emitter to collector and conventional current flows out of the base to turn it on. However, why do they operate like this? Let's look at their internal composition to find out. A NPN bipolar junction transistor consists of two N-type materials that have excess electrons and a thin P-type material with excess holes. Holes are empty spaces where electrons can easily travel into. For more information about N and P-type semiconductor materials, check out my video on diodes. When a more positive voltage is placed on the base compared to the voltage at the emitter, electrons are attracted to the base voltage, causing them to overcome the PN junction. Once the PN junction is overcome, some of the electrons flow into the base, but most of them flow into the collector, causing electron flow from the emitter to the collector. As electronic diagrams often show conventional current, it is important to note that conventional current in an NPN BJT flows from collector to emitter. A PNP bipolar junction transistor consists of two P-type materials that have excess holes and a thin N-type material with excess electrons. When a more negative voltage is placed on the base compared to the voltage at the emitter, holes are more attracted to the base voltage, causing them to overcome the PN junction. Once the PN junction is overcome, some of the holes flow into the base, but most of them flow into the collector. What was just described was hole flow, also known as conventional current. In electron flow, electrons flow into the emitter from both the base and the collector. Now that we looked at how NPN and PNP BJTs work on the atomic level, let's see how they work practically in electronics. Bipolar junction transistors have three regions of operation: saturation, cutoff, and active. In the saturation region for an NPN transistor, the voltage at the base of the transistor is greater than the voltages at both the collector and the emitter. This causes a short between the collector and the emitter, where the collector current equals the emitter current. In the cutoff region, the voltage at the base is less than both the collector and emitter voltage. This causes an open where current does not flow at the base, collector, or emitter. In the active region, the voltage at the base is less than the collector voltage, but larger than the emitter voltage. In this region, there is a specified relationship between the base, collector, and emitter currents that will be discussed later in this video. For a PNP transistor, the voltage relationships are reversed. In the saturation region for a PNP transistor, the voltage at the base of the transistor is less than the voltages at both the collector and the emitter. In the cutoff region of a PNP, the voltage at the base is greater than the voltage at both the collector and emitter. In the active region, the voltage at the base is greater than the collector voltage but less than the emitter voltage. Earlier, we briefly discussed that there was a specific relationship between the base, collector, and emitter currents when the BJT is in the active region. This relationship is as follows. The collector current is equal to the base current times the current gain of the amplifier, represented by the beta symbol. The current gain can be anywhere from 50 to well over 500. It just depends on the BJT model you're using for your electronics project. The emitter current is equal to the base current plus the collector current. If you don't know the collector current, you can solve for the emitter current by having the base current times parentheses 1 plus beta and parenthesis. This relationship applies to both NPN and PNP bipolar junction transistors. While we briefly discussed the voltage relationships between the base, collector, and emitter, it is important to analyze the voltage relationship between the base and the emitter. A BJT is essentially two silicon diodes fused together. Therefore, in order for the transistors to overcome their depletion region and allow current to flow from the collector to the emitter in an NPN or emitter to the collector in a PNP, a voltage difference between the base and the emitter must equal the forward bias of a silicon diode, which is typically between 0.6 and 0.7 volts. Therefore, for an NPN transistor, the base voltage must be approximately 0.7 volts greater than the emitter voltage, and for a PNP transistor, the base voltage must be approximately 0.7 volts less than the emitter voltage. To summarize, if the forward bias voltage is not reached, the transistor will remain in the cutoff region and no current will flow through the transistor. Now let's discuss a couple useful circuits that use bipolar junction transistors. The first circuit I would like to discuss is a simple switching circuit. In this circuit, you have a voltage of 6 volts connected to a load. The load is connected to the collector of an NPN BJT, and the emitter of the BJT is connected to ground. If the control voltage is 0, there will not be enough of a voltage difference between the base and emitter to activate the transistor. Therefore, the transistor will act like an open and no current will flow through the load. Once a control voltage that exceeds the voltage difference requirement is added, the transistor will switch from the cutoff region to the active region, enabling current to flow through it and therefore provide current through the load. To remove current from the load, just reduce or remove the control voltage so that the transistor will switch back to the cutoff region and the load will be turned off. Bipolar junction transistors can also be used in current biasing. In a current biasing circuit, you can use the transistor to control exactly how much current is inputted into the load. Let's look at the circuit. Let's say the max current the load can handle is 1 amp. Given a transistor gain of 100, the base current needs to be 10 milliamps per the base and collector current relationship. Given that the emitter voltage is 0, as the emitter is connected to ground, the base voltage equals 0.7 volts per the emitter base voltage relationship. From there, you can find the required resistor value to get the specified base current using Ohm's law. The resistor value ends up being 43 ohms. But what about the variable resistor in the bottom left of a circuit? What does that do? It's what controls the current going into the collector. If a variable resistor is set to a very large number, such as 100 mega ohms, almost all of the 10 milliamps will go into the base. An insignificant amount of leakage current will go to ground. If a variable resistor is set to 0 ohms, the entire 10 milliamps will go to ground. As no current is going into the base, no current will flow through the load. If you want part of a 10 milliamp current to enter the base of a transistor, you can set the variable resistor to a value that enables some, but not all of the current to flow into the base of a transistor. Let's do a quick example. If you set the variable resistor to 100 ohms, then the current flowing through the variable resistor will be 7 milliamps. Per current divider rule, the remaining 3 milliamps of current will flow through the base, and per the relationship between the base and collector currents, the current going through the load will be 300 milliamps. The last circuit I would like to discuss is the Darlington Pair circuit. This circuit is ideal to amplify the current output. Here's how it works. An input current of 1 milliamp is inputted into the base of a first NPN transistor. Given a transistor gain of 100, the emitter current becomes 1 milliamp times parentheses 1 plus 100 end parenthesis, which equals 101 milliamps. The emitter current from the first NPN transistor becomes the base current of the second NPN transistor. If this transistor also has a gain of 100, the emitter current of the second transistor becomes 101 milliamps times 101, which equals 10.2 amps. The collector current through the load is IE minus IB, which is equal to 10.2 amps
minus approximately 0.1 amps, which equals approximately 10.1 amps. This circuit took a base current of 1 milliamp and quickly amplified it to over 10 amps. To summarize, we learned what a bipolar junction transistor is and how it operates on an atomic level, how it operates on a practical level, and how it can be applied in various circuits.
Hey everyone, I hope you enjoyed this video, and if you did, don't forget to like, subscribe, and click on the notification bell for more electronics videos.